at some point you'll be able to say, oh, look, what we found on Mars is not on our lookup table on Earth. We're not there yet. But, the prediction is we'd see deep branching, right? We have a tree of life on Earth, and everything sort of fits into that tree of life. And Mars would be sort of like what kangaroos are to, North European fauna, recognizable but different.
And how big your sequencer is going to be?
Well, the Oxford Nanopore is a huge company that builds sequencers based on nanopore technology where the DNA goes through a pore, changes its conductance, it weighs 80 grams. There's thousands of these in the field. There's a very enthusiastic user base that goes out and sequences in ponds and, people who have the flu, and it's used constantly for all kinds of things like that. So that's something that could be just massaged a bit. But, NASA has to agree it's a very high-risk thing, right? Because if you go to Mars and say you're going to look for DNA, you could come up with nothing. And they might send instruments that will give a spectrum, a picture, mass, something, an oxidation state.
Well, now there's one other person to talk to, Elon Musk.
Yeah, no, I've been trying.
But that's the rocket instead of the Tesla.
It's way better than a Tesla, much better than humans.
Maybe I can help you there. But I know earlier today we talked about a more simple strategy of trying to find the signs of other type of life on our planet. So maybe it's hiding somewhere where we didn't look yet. So why go elsewhere? Let's just try to see any pockets where alien life can exist. Do you think it's a reasonable strategy?
Yeah, so the modern genomics of DNA world life, serial life, sees evidence of the RNA world as sort of the precursor. There's lots of layers of that in our genomes, of living fossils from the RNA world. So that world was mostly displaced by the DNA world. But the question is there a refugia somewhere where you could see a kind of a living fossil of the RNA world? And, you might want to look in the environment that looks the most like the Earth 3.5 billion years ago. And one of the beauties of Mars is that it doesn't have plate tectonics. And so, we are constantly erasing our history with this continental movement that doesn't exist on Mars. And so you might actually have the remnant of the RNA world there if that's what was actually exchanged between the two. And that would be the most gorgeous thing to discover on Mars, is to be able to do archaeology of bacterial history. I'm not saying it will. It's just not that the prayer.
Lyman, so it seems like the universe might be teeming with life of some sort, at least simple life, and occasionally intelligent life. But from the standpoint of a physicist, how long do you think can life survive in our universe?
Let's see, so if this model we have is right, and we extract it, and we don't end up in a big rip, we'll end up in a long phase of hundreds of trillions of years of a pocket of about 1,000 galaxies, something like that. And who knows what's going to happen after that, right? I mean, who knows whether physics will come in, but just with the accelerated expansion, right, things move away, but we should end up with something like that that's sort of gravitationally bound.
So so basically you give us future years, right?
Yeah, more.
On that note, thank you very much. Nice panel. Sciences at Stanford. He's a pioneer of optogenetics, a way of controlling neurons with light, and Clarity, a technology for making brain tissue transparent to enable detailed imaging. Christopher is a professor of mathematics at the University of Utah. He works on projective varieties, a branch of algebraic geometry with a focus on high dimensions. And Cameron Baffa is a professor of theoretical physics at Harvard University. He is one of the leading figures in string theory and has produced many important and original insights into space-time geometry and black holes. So, discussion one, how much can we know? So, Carl, we human beings evolved to survive in Africa and Savannah. How is it that some of the brains here in the room can understand general relativity?
Well, this is a specific form of a very interesting general question. And it's something that I and many neuroscientists think a lot about. One thing that's clear, and it can be helpful to draw a distinction between what our retina does and what our cortex does, the part of our brain that's most recently evolved common to mammals and greatly expanded in human beings. The retina, its job has been clear for a very long time in evolution, and you can point to and identify precisely maybe 40 or 50 types of cells in the retina, and their jobs are more or less clear. They want to pick up a particular kind of information. They want to detect an edge, for example, in a scene, and that's an important job. It has always been, as long as there have been retinas, that's always been an important thing to detect. So it's a specialist structure. The rest of vision or the side of the brain, the part that does hearing, or the front of the brain has no sensory role at all, but is involved in planning and looking into the future. And it's the same basic structure all the way through. And there are hundreds of thousands of different kinds of cells. You can't point to a particular cell and say this is exactly what the job is. It looks as though it's a generalist model building structure. And so I think that's part of the answer is we're built to be, parts of our brains are built to build models of the world around us.
Christopher, computers are much better than us at arithmetic, for example. Can they do more creative mathematics, like prove theorems in the future?
Well, certainly computers are already helping us prove theorems, right? We're not very good, as you mentioned, at doing hundreds and thousands of computations, and so there are certain theorems that require us to do this many computations, and we do lean on computers to help us get to the end of these proofs. So there's some very famous examples of this, for example, Four-color theorem and Kepler's conjecture. So the four-color theorem is 40 years old, more or less, and there are issues with these proofs, but I think they're getting to be more widely accepted. The next level would be for computers to actually help us check the validity of proofs. Our proofs are getting more and more complicated, longer and longer, more specialized. It gets really hard to get other people to check your proof in detail and to be really confident whether the proof is actually correct or not. So it would be great if there were a way of checking that, and the computer programs actually already exist for this, but you would have to write your proof in a way that it can actually check the computer code, so to speak, and it's very hard to teach mathematicians to do that. So it would be great if there was some software that helps us actually do that, achieve that, and maybe correct errors in the process. This, I think, is a ways in the future. Even better maybe would be to have computers that come up with independent proofs. I mean, this already exists to a certain extent, but it's nowhere near the forefront of mathematics, and the proofs that are produced, they don't give us any insight. They're not produced in a way, it's a sequence of logical steps, but it doesn't give us any insight on the inner workings and on how this can be generalized to other contexts. So I think this is a problem for the somewhat distant future, 40, 50, maybe more years, and it's going to be an extremely hard problem to solve. Producing a computer program that answers new questions that surprise mathematicians and gives insightful proofs is probably almost as complicated as creating artificial intelligence that can truly fool us into believing it's human. Not just for a few minutes, just fool the whole of humanity into believing that it's human.
But do you think in this century, 40, 50 year time frame, it is possible to go away?
Maybe 100 years, but once we solve this problem, I sort of imagine that the artificial intelligence will be able to develop more efficient artificial intelligence, so sort of scary prospect.
Cameron, from physics standpoint, we human beings are a subset of the universe, trying to understand the whole universe. So, do the laws of physics, the way we know them today, provide fundamental limits to what can be known in principle?
It's a tough question, but let me try to imagine far in the future, not this century, but very much in the future. And I don't imagine the question will apply is related to us as our physical being today, how we will evolve and how we can affect it, how we take into account, assuming that we can adapt any way we want somehow. So the question then becomes, since we are basically natural beings and basically part of nature and physics and so on applies to us, so the question becomes related to whether a part of physics can mirror the whole universe in some way. How can it encode? Can the universe be encoded by some subfraction of the universe? That's the way I would interpret the question. Well, that's a tough question, of course, still. But let me just use analogies and what we know in physics today to maybe get some thoughts about that for discussion. So, for example, today we know quantum mechanics is a law of how we describe how the universe works. So maybe if you asked 100 years ago, 200 years ago, maybe whether you can know everything precisely, we may have said yes, why not? We can use Newton's equation and get everything exactly, but we know from quantum mechanics that things are probabilistic. So that's a limit, you could say, of knowledge. Well, we cannot know exactly what's going to happen, but probabilistically. So we see in that context, we're perfectly happy with that now. We just say that's the way it is. So the formulation of what can be known has been reformulated. So the laws of physics can put some limits about what we mean is potentially realizable. Another example from the more modern days, in fact, we heard talk about it in the symposium today, is related to black holes. So again, in that context, as was discussed, if some information falls into the black hole, to retrieve the information, sometimes you have to wait until the whole black hole evaporates, and then it's very difficult, but presumably the information may come out somehow. Well, if it's a sufficiently long-lived black hole, it might take the whole age of the universe for the information to come out. In which case, yes, in principle, therefore, we could know what went in, but in practice, the answer would be no. So there could be such limits. These are just analogies, but there could be similar limits applied to the question whether or not there are fundamental limits. So the laws of physics may place fundamental limits on this, similar to what quantum mechanics does.
And Christopher, what about mathematics? Does it contain within itself the limits to what it can prove?
Well, of course, there's Gödel's incompleteness theorem that says in any interesting mathematical system there are questions that can't be answered. So there'll be some decidable questions and some questions that we can't say if the answer is true or false. And even then, among the decidable questions, it may take longer than the age of the universe to answer them. So the answer is definitely yes, there are limits.
And finally, biology. Are there any hard biological limits to how intelligent we can get?
I don't think there's a hard biological limit in principle. Our brains are, because they're generalist structures, because they don't have to encode all the information that come up with a simple model that has explanatory power, a lot can be done in a fixed volume with a fixed number of neurons. The brain's very good at compressing data, simplifying, creating frameworks. That said, though, that's the optimistic viewpoint. Pessimistic viewpoint is you look at monkeys and chimpanzees, and they have the same basic cortex structure that we have, just a lot less of it, many fewer neurons, less surface area, and they can't, it seems, understand the things we can understand. And so I think it's also likely that without some support of some kind, external support of some kind, which is possible. I think there very well may be things that within our brains themselves we won't be able to comprehend.
What do you mean by support of some kind?
Well, it could take different forms. We all know caffeine makes us more alert, more vigilant, and makes our brains work faster and better in some ways. We live in a very information-rich environment. Our brains are not, we're not evolved in such an information-rich environment. We presumably could tune our brains to accept information at a higher rate, to trust information at a higher rate without repeated presentations. All these things are part of a broader set of strategies that help us learn faster. But in terms of separating the learning and information content from sort of the deep understanding question, that becomes a little more difficult, and the external support might sort of take the form of how mathematicians use computers. It would be a bit of a bridge of some kind that we could build to external processors that allow us to work symbolically and at a higher rate than we could without such support. So I see potentially a future where human beings work together with computers to understand things as well as to remember things.
Do you envision any technology using some implants in the brain, something like that?
So implants, to do that right, one would have to have a deep understanding of the nature of information storage, processing, and representation. And we don't have that yet, but we will get it. And so I think at that point, one could imagine an interface of some kind, whether physical or optical or some other form of energy or information transfer that plays a role in interface and allows that to happen.
And do you think technology you've developed could be as a bridge to that?
It could be. We've worked very hard on optical technologies, and that has a number of useful properties. Optical information flow is fast. Photons can scatter into the brain deeply. They come in different colors, and so you can have multiple channels of information flow that you play and read out optically. It has some disadvantages. Light scattering is a big problem, fundamental limitation. We can't maintain, as you can, by sending a laser through space, where you can maintain its integrity over very long distances. We can't do that light brain due to scattering, which is more or less a fundamental limitation, at least as we understand it now. So I think optical methods are useful. They won't be the full solution. We need some new ideas.
Cameron, sort of at a more fundamental level, if we are very advanced in understanding our universe, many physicists now believe that our universe is just one of many. So if this multiverse is real, do you think we can ever know anything about these other universes?
Well, that's a very interesting question. As we mentioned, in string theory in particular, we predict that there are other kinds of universes. They should, in principle, exist, and we are in one of them, one particular one, but we could have in any host of possibilities. Now, on the other hand, in science, we have a view that if you cannot experimentally check something, that statement doesn't make sense. So if there's no way for us to actually somehow access those universes, then the question becomes metaphysical, whether they exist or not, in what sense do they exist, and so on. So whether we can do it in our current time frame right now is unclear at this point. But there are models in the context, for example, of cosmology, that our universe, for example, could have emerged from another universe in some form of decay, and so in fact some models there are people looking for some imprints in the cosmic microwave background that potentially that thing having happened. So those would be signatures of the would-be universes, which could be the envelope of this multiverse. Whether we can actually access those now, the universes, is a question we don't know yet, if there's such a way, or whether or not we can create such universes within our universe to branch off to different universes again. In principle, I don't see why we couldn't, but we're not there yet in terms of certainly not technology, but even theoretically we still have to understand more deeply what the theory is to see whether that can happen. But in principle, I don't see why not. In other words, that question of whether we can somehow branch out to other universes and get there, maybe a potential answer to Fermi's missing alien problem, and they have found a more interesting universe to be in.
So, Cameron, from the physicist standpoint, how would you summarize everything we talked about and answer the question, how much can we know?
I think probably the understanding of the word knowledge, understanding knowledge itself, what we mean by it, might have to be more refined and defined. For example, suppose I give you a 6 billion digit number and multiply by another 6 billion digit number, and well, can you do it? Well, we can certainly give it to a computer and do it for us, and we get the number out. And did we understand what that number came out? Well, not exactly. We know the rules in which that's happening. So it could be that what we mean by understanding and knowing might be removed from what we now think of internalizing it. So it could be a few steps down the line. Yes, we know roughly how this thing works, and within that context, we know that has been understood by something in some form, just like the way calculator multiplies numbers in some form. So that could be part of it. Or it could be that we have evolved in some way to incorporate the things that we imagine computers do, as we were just discussing, into ourselves in some way, advancing what we could understand as knowledge. So that would be part of it. But at fundamental level, we cannot beat physics. Quantum mechanics are the laws, or whatever. If that evolves our understanding of quantum mechanics or similar things evolve, then that would put limits on us, and we wouldn't know. And we can just by analogy see that quantum mechanics is a limit of knowing, and we have to accept whatever it is. And so whatever that evolves to be, that we are limited.
So it seems to me like somebody needs to know something. So if you, let's say you were trying to do it in one sentence.
There's no limit. There's no limit to knowledge except those imposed by physical laws.
Okay. Christopher, from the mathematician standpoint of view, how do you summarize your answer? How much can we know?
There is no limit to knowledge except our imagination.
Okay.
I really think it's the boundaries of our knowledge are sort of many levels removed from what we imagine right now.
And from the standpoint of biology,
I think there's no limit to our ability to create workable, useful models of the universe and of our brains.
well, on the note, thank you director of the Center for Computational Astrophysics. He was the lead theorist on the WMAP team, which got the Greater Prize this year in physics, which mapped the temperature fluctuations of the early universe. And his other research ranges from dark matter to galaxy formation to search for extrasolar planets. And this is the last panel today, and we're going to talk about his nature symbol. So, Kim, we're going to do first. Explanations of the world have not always been simple, so they used to be myths and legends, pretty sophisticated concepts, but pretty big ones. They could cover hundreds of pages. Scientific explanations seem to do a little better in terms of simplicity, but why do you think they are simple?
I think for me, there's two reasons. The first is, I think that when explanations get very complicated, they're much harder to test, they're much harder to refute. And so you have this very complicated, you can have it like the explanation, the real explanation could be complicated, but establishing whether it's right or wrong may prove impossible because of its complexity. If your idea is simple enough, then it's something that is completely inconsistent with it. It's more like to say it's easier for you to realize you're wrong, and you move on. I think there's a second reason, and that is that we know that very simple processes through iterative operations on those simple processes can give rise to much greater complexity, emergent properties of very simple systems. And so if you see that complexity, you may feel like you need a complicated explanation of it. And yet we do know that if you see this complexity, it doesn't necessarily mean that the underlying operations that are giving rise to it are themselves complex. And I think ultimately, the more simple your explanation, the more universal it will be, and the more capable it will be of generating those complexities through simple operations or very simple processes. So I like simplicity, partly because I wasn't the brightest kid on the school, and I like things to be made simple enough that I can understand them.
Terence now, sitting in the middle, is a professor of mathematics at UCLA. He has brought new insights to a wide range of mathematical fields, including harmonic analysis, combinatorics, partial differential equations, and analytic number theory. And somehow, over time, we just started to use more and more mathematics to explain the world around us. So why do you think it's happening, and why mathematics is so efficient in describing our world?
Well, the universe does seem to have a simple basis, but the primitive objects of the theory are very far removed from our human experience. So we can't use any more sort of regular human intuition to understand particles or quantum waves or fields. And so what's left when you don't have direct human experience is mathematics. I mean, it's a perfect language for dealing with things that you can only see indirectly. And I take Kim's point that simple explanations are preferred, but I have to say it's still critical that we have one. I mean, the default should be complexity. So like you can talk mathematically, you take a random string, say 1 million digits. Normally this is no pattern to it. You need about what you want to describe this string. You need about 1 million characters to describe the string. There are a small number of complicated strings that can be generated from a small rule, but these are really